See, yesterday we gave a definition of a complex number.
You were lost, but
I
I
was
found
lost.
you.
Oh, okay. Good. So a complex number, remember we wrote the set of all complex numbers with this funny C. And so things in C look like A plus BI, where here A and B are real numbers. And, well, we said that this I is supposed to be the square root of -1. But somehow I don't want to think about it that way for a while. The way I actually want to think about it is it's a symbol. And it's a symbol that has the property, I mean this is true, when I cross it out I don't mean it's not true, I just don't want to think about it that way. It has the property that this symbol, if you square it, you get -1. Subtle difference. But later on in your mathematical lives, it'll be important that you make this subtle difference more precise. Okay. So I want to just do a very, very quick sidetrack into abstract algebra to somehow motivate what I want to do later. So this will be very brief. Okay, I know you four have not taken abstract algebra. I don't think you two have either. Is that right?
Abstract algebra?
Yeah.
Last semester.
Oh, did you take it? Okay, very good. So you know what a group is, for instance.
In theory, yes.
Last
semester I knew it.
Did you take it too?
Yeah.
Oh, I thought you were in 331 last semester. I guess I was.
I've taken all my math exams.
Ah, okay.
Hanging out here.
That's right. It wasn't. No, it wasn't 331. It was a geometry class. That's what you were doing.
Yeah, that's what I did.
That's what you were doing. They were both with Jack. That's why I was confused.
Oh, right. Yeah.
Okay. So you, at some point you saw hopefully a definition of a ring.
Yes.
Field. Okay. So what we're going to be getting at here is we want to turn the complex numbers into a field.
Okay.
Okay. So you guys don't know what that means yet. Okay, so I'm going to tell you what that means. Now, a field is, of course, where you grow, you know, your wheat and so forth. But mathematically, it's going to mean something a little bit different. Okay. So let me build this up in two parts, and I'm not going to do this in the most abstract way as I can. But let me start with a set, and I'm going to call it G. So G is a set. And it doesn't need to be the integers, right? They don't need to be numbers. These are just a set of something, right? Set of elements. Right, so G is a set. But what we do have is some notion of what I'm going to call binary operation on the set. What's a binary operation? Well, binary operation is like addition. You take two things, and it spits out something else. You take 5 and 3, it spits out 8. Okay. So it's some rule how to combine two elements of the set and give you, again, an element of the set. Right? It should be in the same set again. So we have G as a set, and I'm going to say, well, we call it dot. Right? This is a binary operation on G. Okay, so I can write down things like A, I'll say times. It's not really multiplication because these aren't numbers necessarily, but I'll write down this thing that looks like a times. And it's supposed to give me some C, and that C is an element of G. Remember this funny E that is an element of. I don't like this pen anymore. We were doing better with the pen. Okay, so now I'm going to start giving you a bunch of assumptions on this binary operation. Because by itself, this binary operation, just knowing you have a binary operation tells you very little. You basically almost play Sudoku with this. Let's assume that first, if I happen to take two of these elements and I multiply them, and then I multiply it by another element of the set, that this gives me the same thing as if I first multiplied the second two together and then multiplied it with the third. And this is called, of course, associativity.
I know. I was like, man, I taught that today.
In math shop, right? You're teaching them associativity of what? Of
Addition.
addition, and what else, of course?
Multiplication.
And a
You
multiplication,
didn't
right?
get that far yet.
No, but you will, of
Oh,
course,
I
right?
did.
What am I? They're teaching this course, Math 000, move, right? Okay, it's the math shop, and it's for people who really need help with the very basics in mathematics, right? And so you teach them things like addition, associative, and multiplication.
Like the identity property.
Yes, and that's exactly what we're going to mimic right here. We're trying to mimic what we know for the integers and for the real numbers right now. That's what we're doing. So the second thing that we're going to write down is that, well, you have this special number, okay, in the set. We're going to assume that there is. There exists, so remember this backwards E means there exists. So there exists some number, and I don't want to call it 1 because I don't want to influence you into thinking every set G should have a number 1 in it. Let's call it E. There exists an element E in G such that, ST for me means such that, if you multiply A and E, or E and A, I don't care what order you do it in, this should just give you A back. So if you were working in the integers, and our binary operation was addition, what would our E be?
0.
It would be 0, right? Because anything plus 0 is anything, right? What if we were under multiplication? It would be 1. Okay, so this is called the identity property. The third thing is that for all, so remember upside A and down A means for all x in G, there exists a y in G such that x times y equals y times x equals the identity. So if we were in the integers under addition, and I start with a 5, what do I have to add to 5 to get to the identity, which is 0? Negative 5, right? And for any number, any integer, I can find a negative of that integer, and when I add those, you'll get back to 0. What if I'm under multiplication? All right? If I take an integer, say 2, what do I have to multiply by to get the identity, which under multiplication is 1? The reciprocal, which is a half, but there's a problem. A half is not an integer. Okay. Now I'm supposed to be, all my things are in one set, so if I'm just talking about the integers, this there exists, it's supposed to be in the same set, it's supposed to be in the integers. So the integers under multiplication do not satisfy this final property. Okay? Under addition they do, under multiplication they don't. This is called the inverse property. So if you have a set with a binary operation and it satisfies these three properties, then we call G a group. And if you want to know what I do for a living, I study something very much related to group theory. Okay? I study objects that satisfy this, which sounds actually pretty, like it's not telling you a whole lot. I mean, there's not a lot of assumptions here. Okay? There's a huge field all devoted to studying these things called groups. And they're incredibly important. Well, they more or less control the universe. Okay. So, there's something about the integers that's interesting. Namely, we have more than one binary operation that makes sense on it. Right? We have addition, but we also have this multiplication. Now, under addition, all these properties are satisfied. So the integers form a group under addition. They're not satisfied under multiplication, right? You lose this, this inverse property. When you lose this inverse property, but you still have these two operations, plus and times, and one more little thing which you all know, but we'll talk about in a second, then you call it a ring. So the integers form a ring, but we want more than a ring. So let me tell you what the next thing we want, which is a field is. So a field, F, is a set with two binary operations. You have two, so think of the real numbers, right? You have plus and times on the real numbers. And let me call them plus and, well, times, to be creative. Okay, such that, well, we're going to have three main properties. The first is that, well, if you just view F as a set with one binary operation, right, addition, that this, actually, I'm going to add one more piece of information just for clarity in the next step. Because it's going to be a group, there's going to be an identity element. Now, under addition, what do you think is a good name for an identity element? Yeah, zero's not a bad one, right? Because identity means you add some, you add the identity element, doesn't change it. Well, zero is a pretty good thing to add, not change it. Right? So let me call the identity 0. Okay. So if you take this set and you just consider this operation plus, you're supposed to get a group. Okay. Actually, we want a little bit more. I'm going to add another word in here. And this is a really technical thing. Okay, but not really. It's something you all want. It's an abelian group. Okay, what's an abelian group? All right, tell me, what's an abelian group?
I don't even remember.
Oh, you don't remember. This is sad.
I just remember that we hated them.
You hated abelian groups? Oh, these are so
Actually,
easy.
they were fascinating, but it's.
No, you can say so many nice things about abelian groups. What's an abelian group? Well,
Oh, isn't it where A and B is BA?
yeah, exactly. Right?
Oh, right.
When you add two integers, does it matter what order you do?
Commutative.
7 plus 8, 8 plus 7. Does it matter? No, it doesn't matter. You can order it, right? It doesn't always work that way. Right? When I say you have a binary operation, I'm not assuming that that's true. Okay? And can you think of a case where it matters what order you do things in?
Division.
Division, yeah, that certainly matters, right? 3 divided by 5 is not 5 divided by 3. What order I put on my socks and shoes? It certainly matters, right?
Depends, are you a surgeon?
I'm a doctor, but not a surgeon. So let's come back over here, and let me just add. G is abelian. Okay, it's also sometimes called commutative, but usually called abelian. Commutative is probably a word you've heard before, the commutative property of addition. G is abelian if A times B equals B times A for all A, B, and G. So if it doesn't matter what order you multiply, then you call it abelian. Okay, this is after the mathematician, just from the first part of this word, Niels Abel. So A-B-E-L. But we don't say Abel, we say abelian.
Is he Norwegian?
He is Norwegian. Yeah.
So
So very, very famous group theorist and mathematician. So we named this after him. But despite it being named after a person, we use a lowercase a.
Disrespectful. I have a question.
Yeah.
You haven't finished this obviously, but I do have a question already in that when you say, because you have two binary operations and obviously the second one is not going to be a group because we know it's not a group, theoretically.
Actually, the second one is going to be a group.
Okay.
Yeah.
Alright, never mind, continue then.
Okay. So, well, almost. It's not exactly going to be a group, but I mean, what I'm going to write down is a group. It's just not going to be the same F. Right?
Okay.
Okay. I'm going to take this F when I know, and think of the real numbers, right? That's the example you have in your head right now. Right? You can add real numbers, okay, and they stay real numbers. There's associativity of addition. There's an identity element. There's an inverse element. Oh, you're trying to follow me with the camera, aren't you?
I quit.
Don't worry about following me so much. I move too fast.
Yeah.
Yeah, no, I'm too good at that. And it won't focus fast enough. Yeah, that's true. Okay.
They just started writing over there again, and I was
No.
like,
The next thing I want to consider, okay, leave a little room. Okay? You have to leave some room here. I want to consider f under multiplication. So think of the real numbers under multiplication. Now, if you multiply two real numbers, you again get a real number. Okay? Multiplication is still associative. There's an identity element, right? 1 times anything is that anything. Inverses, right? Can you take any number and there's a reciprocal, right?
but it's not an integer.
In the reals, yes.
We're in the reals. Does
Oh.
every real number have a reciprocal? Yeah, pi has 1 over pi, 6 has 1 over 6. But
They're not integer.
0, right? 0 doesn't have a reciprocal. Okay.
Damn, 0.
So no matter what we do, we're never going to be able to, as long as we have this 0 floating around, you can't divide by 0. So what we do is we just say, well, forget about 0, and just look at what happens if you toss that out. Okay? If you toss out 0, I'll put 1 in here, give a name to the identity. This should be an abelian group. Okay, but now there's a third thing, which, well, there's a property that you learned when you were kids. So you learned the associative property, you learned the commutative property. What's the last one? You probably taught it in math.
Distribute.
The distributive property, right? What is the distributive property? Why is it important? The distributive property tells you how to relate the two binary operations. They're not completely independent of each other. That's the point. So what this should say is something like this. If you multiply a times b plus c, then this should be the same thing as a times b plus a times c. So this is distributivity. And normally when you write down these axioms, you're doing it in a more general setting of a ring, and you have to write it on both sides. But because we're assuming we're already in an abelian group under multiplication, we only have to write it on one side. Don't worry about that. So this is what we call a field. So the real numbers form a field under addition and multiplication. What about the rational numbers? Well, let's see. There's two obvious binary operations still, plus and times. Now, let's see. Under addition, okay, you add two rational numbers, it's still rational. Okay? It's associative, sure. The identity element is still in there, right? Because a 0 is a rational number. Inverses, sure. If you take a rational number and you can take the negative of it, that's still a rational number. So that's an abelian, and of course you can add in any order you like. So it's an abelian group. What about under multiplication? Okay, remember we get to toss out 0. If you multiply two rational numbers, it's still rational. Associativity multiplication, of course, still works. 1 is a rational number. And, well, if you don't want to invert 0, sure, if you take a rational number and invert it, it's still a rational number, right? Invert a fraction, still a fraction. Right. So, and of course you can multiply in any order you like. So it's an abelian group. And distributivity, well, we know that holds for the real numbers, so it must hold for rational numbers as well. It's called a fortiori. So the rational numbers actually form a field. That's nice. So real numbers form a field, rational numbers form a field. The next step down is the natural numbers, or rather the integers, right? And we said the integers do not form a field. Why? Well, they form an abelian group. They satisfy distributivity. But if you take the integers and you get rid of 0, right, you don't have inverses under multiplication. Because the inverse of 2 is 1/2, which is not an integer. So it's not a group. It's abelian, but it's not a group. So the integers are not a field. They're just what we call a commutative ring. Actually, you can go so far as to say they're a Euclidean domain, but that's just a lot of jargon for you right now. Okay. Okay, so this is a general setup, and you can start with any set, define operations on it, and say, do I get a field? And that set may not have to include the numbers that you're used to dealing with. And so as we progress further on, not just in this class, but in your mathematical courage, you will see all sorts of fields that are very different from what you would expect. It's not just the rational numbers and the reals. There's a lot more out there. Field theory is a lot to it. Okay. So our goal now is to build a field out of the complex numbers. Okay? Which means we want to define two binary operations, a plus and a times, and we want to show that they satisfy these properties. Okay. That's our goal. This is the background for it. Any questions?
Yeah. Well, this is what I wanted to ask before, is that it doesn't matter which one of your binary operations satisfies 1 or 2, right? It could be any one.
Yeah, I mean, as long as the distributivity property holds in this way, then
Then
yeah.
it doesn't matter. Okay, my next question is,
It's just a naming convention anyway.
what I was wondering is, does the 0, I mean, like, suppose you weren't using 0.
Yeah,
You
call
were
it
just
E.
using an E, right?
Yeah.
Would that mean that in the second one, you would do the F without that E?
Yep.
Okay.
Yep.
But E is different in the second one. So
This
No,
is,
no, no,
This
what
is
I'm
supposed to
saying
be the
is-
same 0 as this
Right,
0.
yeah.
Yeah. Yeah. What I'm doing here is removing the added. This is called the additive identity.
Right.
This is the multiplicative identity. So I'm removing the additive identity. And well, this isn't really the appropriate place for it, but in a course in abstract algebra, you, for instance, will show using the distributivity property. And once you've defined this additive identity, then it's going to have a multiplicative property, namely 0 times anything has to be 0. Okay? So that's why this has such an important role in both of these. All right, there's one of the reasons why. That's why it's not going to have an inverse, no matter what you call it, E or 0 or Christina. Okay, so let's go to work, right? So the first thing is we have our set of complex numbers. We know what they look like. They're all these A's plus BI's. We need to define two binary operations. So how about we start with a plus? All right, so let's let A plus BI and C plus BI be complex numbers. So we're going to define what we mean by A plus BI plus C plus DI. And while we're at it, we may as well define what we mean by A plus BI times C plus DI. We need two binary operations, so we might as well define this. Okay, so you have choices. There's a lot of choices you can make in how you want to add these things together. You could say, let me think, I want to add the A and the D, divide it by 2, and that'll be my real term. And then I'm going to take the B and the C and the D, raise them all to the third power and multiply them together, and make that my imaginary term. You could do that. That would be a perfectly legitimate binary operation. Right? It would give you a new complex number, sure. Why is it not a good idea? Well, remember in the end, we want whatever we choose to satisfy these properties over here. So we want to define it in such a way that all these properties are going to hold. So there's kind of a naive way to add these things together, and it's going to turn out to be the correct way, which is, well, you just add the components. Right? Take the reals and add them together. Take the imaginaries and add them together. So let's see. So this would become A plus C plus, well, you have BIs and DIs, so add them together, you should get B plus DIs. And, well, to get the product, kind of a natural thing to do would be just multiply these out, right? Just FOIL them. So A times C, we'll just do a little scratch work down here. A times C plus A times DI plus BI times C, which we could write as BCI. And I'm actually hiding something right there. Okay. Plus, okay, BI times DI. So that's B, D, I squared. I'll give extra credit to anybody who can figure out what I just hid under the rug.
Minus BT.
So okay, so the next step, of course, is this, right, what is I squared? Right, well, that's what I said at the beginning, right? We want to think of this I squared as negative 1. Right? So I can make this plus into a minus and just get rid of this I squared. Right? I squared equals negative 1. So let's see. So I have an AC and a minus BD. And then I have an ADI and a BCI. So AD plus BCI. Okay, so that's how you multiply them. Okay, that's the formula, but nobody remembers it. Yeah.
We don't know if they're valuable.
Ah, that's exactly the thing, right? What did I do here, Heidi?
You switched it around.
I
You
switched
can't do that.
my B. We know we can move the B's and the C's around, right? Those are fine. Those are just real numbers. But I moved the C and the I and the B's and the I's, right? I moved those all around each other. When I said, for instance, BIC, I should have written BIC. But I said, no, well, this is clearly the same as BCI. Okay? Well, this only is true if IC equals CI. Okay, so that's an assumption that we put into the game. Okay, so we have an assumption on complex numbers that we want. Technically it's not actually an assumption. It's following from defining things in this way. Okay, but let's write it down as an assumption. Is that AI equals IA for all real numbers. So I squared equals minus 1, and I commutes with every real number. So we're going to make that assumption. Okay. Like I said, we're not really going to memorize this formula. Right? You just know that when you see two complex numbers, you can FOIL them out. That's what you want to remember. Okay. Now, we have all this stuff, right? We have all these things to check. Ballpark, how long it would take to check all these things?
Long time.
A long time. Let's not do that. All right, let's just talk through it a little bit. Okay, maybe we'll pick one or two of them. Okay, so let's see. First, under addition, to be an abelian group, okay, it needs to be a binary operation. Sure. Right? This does give you a new complex number. It needs to be associative. Okay, well, you can see pretty clearly if you added 3 of these together, the associativity would actually come down to the associativity of the real numbers. Right? Because you'd have just A plus C plus E or something, right? And you'd have to put parentheses, and you'd have to move them around in the right order. It would just be a pain, right? But you can see how you would do it. Okay. Let's see. Next, you need to have an identity. Okay, so an additive identity. So what can you add to A plus BI and get out A plus BI?
0.
0, right? Remember, we use 0 to represent 0 plus 0i. That was a complex number. So 0 is the identity. What about an inverse to 0. Okay, so I start with a plus bi, and I want to add something to it and get out 0.
Negative A minus B.
Negative a minus bi, right? Because watch, a plus bi plus negative a minus bi equals, well, you do a minus a is 0, bi minus bi is 0, I is 0. Okay, so it has additive inverses. Okay, cool. So it's an abelian group under addition. Okay, let's check multiplication. Let's see. If you multiply, well, by our definition, there again, it's a complex number. Good, it's a binary operation. Associativity. Ooh. Now this is not quite as clear, is it? Right? Here it was very easy. You knew it would just come down to associativity to real numbers. Here, this requires some work. So I encourage you to do this. Everyone should do it once in their life, and only once. Which is why I've never done it. Because I did it once. Maybe more than once. But, okay, you have to check it. It works, but you can see it's going to be a little more intensive to write all out. Okay, what about an identity element? What can you multiply by a plus bi and get out a plus bi?
1 plus 0 I.
1 plus 0i, right? Which we just write as 1. Let's check. A plus bi times 1 plus 0i. We'll do it really pedantically. We'll follow the definition. The definition says you do a times c. Okay, that's a times 1. Good, that's a. Minus b times b. That's minus b times 0. That's 0. Good, so you just get a. Plus ad. That's a times 0. Okay. Plus bc. That's bi times 1. Or b times 1. So that's b I. Ah, good. Okay, it worked. Okay, so we have an identity. Okay, now the last thing is we need an inverse under multiplication. So we need to be able to do 1 divided by a plus bi. Okay, so that we need to figure out. What's 1 divided by a plus bi? First place where the associativity is trivial. It's a lot of work, but it's trivial, right? In the sense that you know exactly what you have to do to check it. You just have to write it all down and make sure all the equations are right. This one feels non-trivial. Okay, so we need an idea.
Times a minus bi, top of the bottom.
This is a very good idea. Why do you have this idea?
Because if you have two i's times together, you get minus 1. Gives the I.
This is Kaiway's suggestion. Multiply by a minus bi on top and bottom. Okay, this is what you do when you're trying to rationalize denominators. And the reason why you do it is because you know that you're building up a difference of squares in the denominator. And, well, let's see. We just said this definition basically says you can FOIL. And foiling would tell you get a difference of squares. So you just have a squared minus this thing squared, so bi squared.
That's B squared.
So what's bi squared? Well, it's b squared times I squared. And I squared is -1. So this actually is minus b squared. So we get a squared minus b squared. And on top, it's really easy because we know how to multiply by 1. This is a minus bi. And so if we simplify the bottom, we get a minus bi over a squared plus b squared. Okay, so let's check, because what did it really mean to have a multiplicative inverse? It means you could multiply a plus bi times something and get 1. Okay, so let's check. Let's do it over here. Let's multiply a plus bi times a minus bi over a squared plus b squared. Actually, this isn't really written in the right form of a complex number, by the way. Complex number is supposed to be a real number plus a real number times I. But I can fix that. I write it as a over a squared plus b squared minus b over a squared plus b squared times I. It's the same thing, right? When you have a fraction, you can split up in the numerator. So I'm supposed to multiply a plus bi times this thing. And it's supposed to come out to be 1. Are the odds good? They better be.
Why not?
Let's check. Okay, well let's see. So here we get a times this bit, which is between a squared on the top. And then here you get an a times this bit, which gives you a minus ab on the top. But this next one is going to be a times b. So you'll get a minus ab and a plus ab. And they're all over the same denominator, and they're both times I, so they cancel. Okay, so then the last thing you're going to get is minus b, okay, you get a b times b, that's b squared. And you have an I times I, that's I squared. So that's just a minus 1. And you already have 1 minus 1, so you get 2 minus 1 plus 1. So you just get plus b squared over a squared plus b squared. Since they have the same denominator, you can add them together, and you get a squared plus b squared over a squared plus b squared. And that equals 1. That works. Okay, cool. So this is how we're going to this is how we're going to divide. Okay? We're just going to, dividing by a plus bi is the same as this. Okay? So that shows us that we have an abelian group, right? When we give rid of 0, at least, under multiplication. All right. Now the last thing is distributivity, and again, this is one of these things like associativity. You can see how to check it. You just choose 3 different complex numbers and add 2 of them together and then multiply it by a third. And then separately multiply 2 of them together, multiply the other 2, and then add it together and make sure that you get the same thing. Okay. I won't do it out, it's quite boring. But it works. Okay, so the distributive law holds these things. So in the end, we get that complex numbers form a field. Theorem. The complex numbers with addition and multiplication, with the additive identity being 0 and the multiplicative identity being 1, forms a field. So on the first homework, you get some practice manipulating these things. But, that's one part of the first homework anyway. It just takes a little bit of time to manipulate and get used to it. It's not hard. Okay. So something that we did in here, I want to go into a little bit further, which is, well, we multiply top and bottom by this a minus bi in this case to take care of this division problem. And we give a special name to this number vis-a-vis this number. Namely, we call it the conjugate, or the complex conjugate. So let me define that. So if we let a plus bi be a complex number, the complex conjugate of a plus bi is a minus bi. And we denote it by a plus bi bar. We write a bar over a plus bi. So whenever we write a bar, I just mean take the imaginary part of the number and make it negative. Now let me give you an example to say that I don't mean exactly what I just said. So 2 plus 3i bar is 2 minus 3i. 2 minus 3i bar is 2 plus 3i. Okay, so I said, well, you should negate the imaginary part, or you should make it negative. But if it's negative, right, you want it to become positive. So when I say I really mean I want you to negate it, right? Doesn't matter if it's positive or negative to start. Okay. But what that means is the following. If I start with a complex number, and I take its conjugate, and then I take its conjugate again, and get back what I started with. You do it twice, you get back what you started. So this is I'll say what I'm going to say in a second. Okay, now this conjugate process has a couple of very nice properties. And for you two, they're summed up by saying that it's a ring homomorphism. So let me write the properties down. Now, let me let me just to save a little space, at least for the moment, right? Let's say u and v are complex numbers. Okay, so I'm not going to write a plus bi for a while. For a while, I just need a few minutes. Not even that. Okay, just take two complex numbers, u and v. And now let's say I add two complex numbers together. And then after I add them together, I get a new complex number, and I take its complex conjugate. What you would like to hold, and what we'll show does hold, is that this is the same thing as if you first took the complex conjugate of u, then took the complex conjugate of v, and you added it together. And a similar thing should hold for multiplication. If I multiply two complex numbers and then take its conjugate, this is the same thing as if I take their conjugates individually and then multiply. And of course, this is exactly what you're looking for in a ring homomorphism. Only this bar usually was like an f. F of u plus v equals f of u plus f of v. F of u times v equals f of u times f of v. Actually, to be a true ring homomorphism, you really want it to also satisfy that 1 bar equals 1, but it does, right? What happens if you take the complex conjugate of a real number? Right? What's the complex conjugate of 5, for instance? It's just 5, right? Because 5 is 5 plus 0i. Complex conjugate is 5 minus 0i, which is just as bad as 5 plus 0i. Why not just as good? I'm reading The Phantom Toll Booth to my kids, and there's a really great line in it. One of the kids said, something happened, he goes, well, that's just as bad. And the other guy goes, well, that's also just as good.
That was painful.
Phantom Toll Booth's a great book. This also works with 0, by the way. But that actually follows from this property. Okay. So let's prove these two properties. Just get a little more feeling for working with these things. All right. So to prove this first one, well, I really can't work with u and v as they're written. I need to choose, A plus BI, like that. So let's look at A plus BI, right, plus C plus BI, and then we're going to take the complex conjugate of it. Okay, so we're going to add two of these together. Fine, well we know how to do that. You do A plus C, and then you do B plus DI, and then we take the complex conjugate. And all the complex conjugate does is negate the imaginary part. Right? Negates this part with the I. So this becomes A plus C minus B plus DI. Okay, no problem. Fine, well, let's check the other side. You do A plus BI, and you conjugate it. And you do C plus DI, and you conjugate it, and you add it up. What do we get? Well, let's see. The conjugate here is A minus BI. And the conjugate here is C minus DI. And if we add those together, we get A plus C. And then, well, we can see we have minus BI minus DI. Well, that's the same thing as minus B plus D. Okay. Minus B minus D, you can pull the minus out, make it B plus D. Oh, good luck, they're the same thing. Okay, so it works. Okay, I won't bore you with the second one. It's the same thing, right? You got to work it out though. All these things take, you should do them the one time.
I thought that you could also, though, like for instance, if you looked at the U plus V, and you're taking the conjugate of that, couldn't you also then do U minus V?
Mm-hmm.
But that wouldn't work for that.
Let's see. So let's say we do U minus V bar.
No,
That's not what you're looking at.
No. What I mean is that if you take, like for instance, if you're taking the conjugate of U plus V, you could just do U minus V.
No, that's not right.
No? Okay.
No, if it's A plus BI, it becomes A minus BI. But if the conjugate of U minus V, of U plus V was U minus V,
Yeah.
well, let's take a very special case where U is 0.
Okay.
Okay? So in that case, you would just have V bar equals minus V.
Right.
But that would mean if V was A plus BI, then A plus BI bar would just be minus
Right.
A plus BI, but that would negate the A as well as the B.
Right. So it doesn't work. But
Doesn't work.
is that the case sometimes where that works?
It only will work if V is pure imaginary number. And because as soon as you negate the real part, it will be wrong all the time.
Right.
Yeah. So the only time it can possibly work is if V just looks like, XI.
But does that work with, let's say, not talking about complex numbers? Because I thought I learned that somewhere. Like, if you're using sets, would that work?
It's not clear. I mean, we don't know what's the conjugate of a set.
Oh, okay.
Right.
Gotcha.
How did you do?
So when you have imaginary numbers in there, you take conjugate, you put the bar on the top, the conjugate should be minus.
Minus the imaginary part.
But when there's no imaginary part, you take conjugate, it still be the same.
Yeah, exactly. So right, if you just have 2, you take the bar, right? Well, this is the same as 2 plus 0i. So the conjugate is 2 minus 0i, which is still 2.
So the U and V, there's no I in there. So
Well, when I write this, I mean U and V are complex numbers. This is hiding an A plus BI in it. Instead of writing A plus BI, just write U. So this is a way of shortening it up to make the formula look nicer. Okay. But what it's really saying is if you add 2 complex numbers, one's A plus BI, one's C plus BI, like this, right, and then you conjugate it, it's the same as conjugating them individually and then adding them together. And the same works with multiplication. Right. Okay. Any questions? I like questions, so don't get me wrong. And, I'm very happy with questions. Okay, let's push this a little more. This conjugate's going to be very versatile, very useful. So let's see, if we take a complex number u and we multiply it by its conjugate, I'm curious what we get. Yeah, so let's work this out. So if u is a plus bi, and we do a plus bi times a plus bi bar, then, well, this is exactly what Kaiway suggested we do when we found the inverse of a plus bi, right? Because this is a plus bi times a minus bi, which is the factorization of a difference of squares. And we saw which factorization it was, right? I mean, what the difference of squares was. It's funny because here a difference of squares actually becomes the sum of squares. Okay. It's a squared plus b squared. Now, this a squared plus b squared looks familiar, especially to those of us who were, I don't know, a few hours ago at 265. Right? What is a squared plus b squared?
C squared.
C, no, it was not c squared, Kaiway.
squared.
D squared. Yeah, okay, let's draw a little picture. Okay, this is 0, 0. Right? We're in the complex plane. And I stick an a here, and it'll be over here. And so this point over here is a plus bi. Let me draw a little arrow there, a little vector. So when I do this, I actually create a very nice right triangle. And what's the height of that right triangle? B. And what's the base of this right triangle? A. And so what do we know about the length of this vector?
We should ask Pythagoras.
We should ask Pythagoras. Well, it's going to be the square root of a squared plus b squared, right? Which is exactly the square root of that number. Square root of a squared plus b squared. See, everything always comes down to Pythagoras.
Knew
Okay.
he was a genius.
So this was our u. We're going to give a special name to the length of the vector that goes, or if you like, the ray. Well, rays, I guess, don't stop. Instead of the vector. The vector that goes from 0, 0 to whatever complex number you put down. And the way I'm going to write it is it's like the absolute value. So the absolute value is here, the square root of a squared plus b squared. Okay, it's just the length of this vector. And it shouldn't bother you too much that I use the absolute value signs, because, for instance, today we saw in class that the absolute value is how you measure distance. Okay. What's the distance between two real numbers, a and b? Right, remember, it was the absolute value of a minus b. We'll take one of those numbers to be 0. Well, then it's just the absolute value of a. Okay, well, here we're doing the same thing. The absolute value here, right, the length of this vector, it's just the distance between the point in the complex plane that you've chosen and 0. Okay, that's why we use this symbol. It makes good sense. Okay, so this will often be called the magnitude of u. So this is nice. It allows us to answer our question, what is u times u bar? U bar equals, all right, what is u times u bar? But, oh, I should mention, this is also sometimes called the norm of u. What is it? Well, remember we did this computation, right? If we write u in this way, we do u times u bar, then we get a squared plus b squared. And, well, here's our a squared plus b squared, it's got a square root on it. So if we square this, we get exactly that. So this is equal to the norm of u squared. Okay. This is nice. Okay, now let's go back and do something a second time that we've already done. We want to compute the inverse of a complex number u, right? The reciprocal. What is 1 divided by u? So before what we did, before we did a plus bi, right? And Kaiway said let's multiply by a minus bi, which is, we now know the complex conjugate, okay? Which we can write as u bar. Okay, so we multiply top and bottom by u bar. So this equals, well, on the top you get u bar, and on the bottom you get, well, u times u bar, which we now know. It's just the norm of u squared. And one thing to mention, u bar comes from u. U is a complex number, so u bar is a complex number. But the norm of u squared, what kind of number is the norm of u? Well, there's no i's in here, are there, right? It's just a real number. So all you're doing here, this is a complex number. This is just a real number. And that's the part, remember when we broke it up, we had this a squared plus b squared on the bottom. We pulled out. So this is another way to write the inverse, all right, of a complex number. U bar over the norm of u squared. So somehow the inverse is u bar itself. But when you do that, you get a little bit extra of a real number. It's not quite right. When you multiply them together, you end up with this u bar squared, so you have to divide out by it. Okay? So sometimes you think about that as normalizing something. Right? In statistics, you do that a lot, where you try to make sure that the mean maybe is 0 or something. There's some number you want to set as the mean, so you divide everything by a constant number so that it all normalizes to a certain spot. Okay? So that's all we're doing here. We're somehow normalizing it. And I'll say more on that in just a second, but that's going to be one of the reasons why the word norm is popping up here. Not because the guy who invented this stuff watched Cheers. Maybe you guys are too young for Cheers jokes. You ever see Cheers? You live in Boston, you should watch Cheers or something.
I've seen it once or twice.
Yeah. Big fat guy on a bench named Norm. He walked into the bar all the time and everybody goes, Norm!
Yeah, I know.
Okay. Now,
You're showing your age.
I can't help that.
I didn't want to say it.
I can't help that. When you get to be 43, you've seen a lot more than your students.
This is a very true statement.
What?
You're 43.
You don't think I'm 43?
No.
You're not 43.
You're not 43.
But they don't know that. How old do you guys know how old I am?
No.
No, how old do you think I am?
Oh, I
You're
hate
30s.
thinking. say 35, some around there.
I just said in your 30s.
In my 30s, so low 30s, high 30s. Don't worry, your grade doesn't depend on it.
Right in the middle.
Not that
Not that much, yeah. Mid 30s, 35, you think, huh?
I don't know. It's in the. I know it's in the 30s somewhere, and 35's in the middle. So.
How old are your kids?
2 and 4.
Oh, 31, 32, 30.
33.
Are you 34?
No.
I'm 30.
Don't worry, he drops the lowest grade, so. But that's it.
No, I think we're failing everything from now on.
I know, right?
Alright, so let me show you another reason why I want to call it the norm, and it again has to do with normalizing. Let's say I take a vector, or a complex number u, and then I divide it by its length, right? The length of this vector, right? Which is the number, just this number, I just divide it by it. Let's see what you get as the new length. So let's take the length, right? So the length we get by taking the absolute value of u divided by, well, I want to divide by its length, all right? I take my complex number, I divide by its length. Okay, well, since what I would like to do, here's what I would like to do. I can't justify it yet, but I would like to do this. Okay, so I use an exclamation point when something needs to be justified. I would like to say that the absolute value here, right, this norm, works just like the regular absolute value. And the regular absolute value has a wonderful property. If you take the absolute value of something divided by something else, it's the same as the absolute value of the top divided by the absolute value of the bottom. So I'd like to do that. So this is the absolute value of u divided by the absolute value of the absolute value of u. And then I want to say, well, this is just a number. That's a real number. So when I take its norm, that's very easy to compute. The length of the number is just how far it is on the real number line. So nothing has changed. The absolute value of the absolute value is itself. So this is the absolute value of u divided by the absolute value of u, and this equals 1. This is what I would like to say. And this is all true. This is all true. But we don't know that property yet. So let's be... So, I have to put down this. Okay, well, let's see. The norm of a plus bi, we actually know what that is. It's the square root of a squared plus b squared. So I can actually write this as a plus bi over the square root of a squared plus b squared. And then I can break this up into two fractions. A over square root of a squared plus b squared, and b over the square root of a squared plus b squared, all times I. Fine? Didn't want to do it. Christina made me. I want to take the norm of this, and the norm of a complex number is the square root of the real term squared plus the imaginary term squared. Okay, we're not including the I. So let's see. So this is the square root of this thing squared. So let's see. This thing squared is a squared over, well, the square is just going to kill the square root. That's nice. So I get a squared over a squared plus b squared. Plus, and over here I get b squared over a squared plus b squared. Oh, this isn't so bad. They have the same denominator, so I can combine them, and the top is again a squared plus b squared. So it's actually a squared plus b squared over a squared plus b squared, which is 1. Square root of 1 is 1. Good. It works. Cool. So what this says is, let's say I start with a complex number u. And I want to find a complex number u, or v say, which goes in the exact same direction. Right? It's on this line, but it has length 1. Right? Why would I want to have something of length 1? Well, I like being on the unit circle. You know how I feel about the unit circle, right? So I want to be on the unit circle. So if I do that, I want to have some point here, right, where this is length 1. And what this says is the way to do it is to take my a plus bi, my u, and divide by the norm. Because the norm, dividing by a number doesn't change the direction. Okay? If I multiply this by a constant, all it does is move me along this vector. If I multiply by a negative constant, it makes me go in the other direction. So this right here, this would be u divided by the norm of u. So this is a useful construction. You have some complex number, and you want to somehow project it back onto the unit circle. You just divide it by its norm, or its magnitude, and that'll put you back on the unit circle, right? This is something close to a circle radius 1. Do we have this on camera? I don't think you're seeing the circle, are you?
No, I am.
There was the circle that you heard me talking about. Nice. Now, see? Unit vector. Unit vector, by the way, vector of length 1. Unit 1. That sort of thing. Okay. Alright, so again, I'm going to tell you a lot of things that I'm not going to write on the board because they're routine calculations. Okay? All these things are basically routine calculations, right? You don't really need me here to do them. You know, I didn't. My PhD doesn't tell me how to do these things, right? I mean, you can do these things without a PhD. It's okay, right? My PhD is to better things, right? Okay. So I'm going to tell you a lot of things that I want you to check, and you should check these things. Okay? You should do them. And they're not hard. Okay? They're routine. So let me give you something to check. I want you to check that if I take two complex numbers and I multiply them together and I take their norm, that this is the same thing as taking their norms individually and multiplying. So please check this. Incidentally, once you have this, let's assume that we've proven this. What if I want to do u divided by v? Well, I write this as u times 1 divided by v. And then I break this up as u times 1 over v. So now I've reduced it. I only need to figure out what this bit is. Okay, but I know what 1 over v is, right? You see, you're looking at the right spot, right? Okay. If I want to know what 1 over v, it's just the norm of, it's a complex conjugate of u over this norm squared. So I could do that. Well, okay. I guess that probably doesn't actually. Well, no, it does help the problem. Okay. So this becomes, well, this is just a real number. So let me write it out here. 1 over the norm of u squared times
V.
Oh, v. Whoops.
No, that's
No,
you.
no, that's
Oh,
you.
that is you. No. Yep, there's my u. There's my v. There we go. Now, if I take a vector, or a complex number rather, and I lengthen it or shorten it by a constant, by multiplying by something, then, or that is, I multiply by a constant and I say how long it is. That's the same thing as seeing how long v was and then dividing it by this constant. So I can pull, this is just a real number, I can pull that in and out. There's no problem there. This is 1 over that times, there, whoop, I forgot. Okay, or I can I won't mess with the U yet. Let's just figure out what this is. So what's the norm of V bar? What's the size of V bar? Well, think about what you do when you take the norm. You do a squared plus b squared, and you square root it. When you do V bar, you make it a minus b, but when you square minus b, it doesn't change what v squared is going to be. So this is actually the same as what? It's just the norm of v. Right? So norm of u bar equals the norm of u. So this is now u times 1 over the norm of v squared times the norm of v. So now I have a norm of v over a norm of v squared, so one of these is going to cancel. Okay, so I just get the norm of u divided by 4, which is the thing that we said over here we needed to be verified, is that we could break up a norm when we had division. Yeah. Of course, I'm assuming here v is not 0, but I think that's clear. I mean, I'm assuming. Okay, so you only need to show the multiplicative property. Okay, so you should check that. And you'll just need to give names to these things, a plus bi and then c plus di, and then check. Or, well, it's possible you might be able to use some formula like this to do it. Check it. Okay, I think that's enough for